group capacitors for required capacity and voltage rating. Hi everyone. In this video session, let's group capacitors for required capacity and voltage rating. Objective: at the end of this video, you will be able to connect the capacitors in series and parallel combinations. Let us discuss the series connection of capacitors. When capacitors are connected one after another, it is called a series circuit. In the given circuit, above the right-hand plate of the capacitor, C1 is connected to the left-hand plate and C2, whose right-hand plate is connected to the left-hand plate of the third capacitor, C3. In the case of a polarized capacitor, it should be connected properly with a correct polarity, like the negative terminal of the C1 connected to the positive terminal of the C2, the negative terminal of the C2 connected to the positive terminal of the C3, and so on. In case of non-polarized capacitors, you can connect it series at any side, since these capacitors, as we discussed earlier, in a series circuit, the current remains the same, whereas in a series connected capacitor, charge Q remains the same. The farad is an extremely large unit of capacitance. In most electronic and electrical equipment, capacitors with farad values are not used. Most capacitors are generally rated in microfarads MF, microfarads MF, and nanofarads NF. 1 microfarad is equal to 10 raised to the power of minus 3 farad is equal to 0.001 F. 1 microfarad is equal to 10 raised to the power of minus 6 F equal to 0.000001 F. 1 nanofarad is equal to 10 raised to the power of minus 9 F equal to 0.00000001 F. Let us put it into practice. Let the values of the two capacitors C1 and C2 be 2 and 4 microfarads respectively. Connect them in series. To find the equivalent capacitance of series connected capacitors, substitute the values in the formula. C is equal to 1 by 1 divided by C1 plus 1 divided by C2. C is equal to 1 by 1 divided by 2 plus 1 divided by 4. We get that the total or equivalent capacitance is equal to approximately 1.33 microfarads. Now connect the AC voltage source 230 volts 50 Hz to the circuit, a moving iron ammeter 0 to 1 amp, and an on-off switch S, all in series with the circuit. Take 3 moving iron voltmeters V, V1 and V2, each ranging from 0 to 300 volts. Connect voltmeter V across the circuit and voltmeter V1 and V2 across the capacitors C1 and C2 respectively. Close the switch S. Note the ammeter and voltmeter readings in the tabulation. Replace the capacitors C1 and C2 as given in the tabulation. Verify the measured readings as follows. Calculate the value of capacitance minus reactance. Xc is equal to 1 by 2 pi Fc. Substitute 3.14 for pi, 50 Hz for frequency, and 1.33 microfarad for C, since we already calculated the total capacitance as 1.33 microfarad. So we get capacitance and reactance Xc is equal to 2394 ohms. Calculate the current using the formula I is equal to V by XC. I is equal to 240 by 2394. We get 0.1 amps or 100 milliamps of current. Calculate the voltage V1 and V2 appearing across the C1 and C2 from the formula. V is equal to I into XC. Similarly, V1 is equal to I into XC1. V2 is equal to I into XC2. Substituting the values, we get V1 is equal to 0.1 into 1592. V1 is equal to 159.2 volts. V2 is equal to 0.1 into 796. V2 is equal to 79.6 volts. When you add V1 and V2, you get 239 volts, which is approximately equal to the input voltage of 240 volts. Ensure the calculated values are approximately equal to the measured values. Let us discuss parallel circuits. Connect one end of the capacitor together and the other end together to make the parallel connections in the capacitor. If it is a polarized capacitor, connect all the positive terminals of the capacitors together and all the negative terminals of the capacitors together. Ensure no polarity in the capacitor is connected wrongly. In the case of a non-polarized battery, you can connect any two sides together and the other side together since they have no polarity. Connect the two capacitors C1 and C2 in parallel. The total or equivalent capacitance in parallel. Connected capacitors can be calculated using the formula C is equal to C1 plus C2. Simply just add all the capacitor values that are connected in parallel. Let the capacitor values of C1 and C2 be 2 and 4 microfarads respectively. The total capacitance for this circuit is 6 microfarads. Connect an AC 230 volt source with a 50 Hz frequency to the circuit with switch S. Connect a moving iron ammeter ranging from 0 to 1 ampere in series between the voltage source and capacitor circuit. Connect a moving iron voltmeter ranging from 0 to 300 volt across the capacitor circuit. Close the switch S. Note down the ammeter and voltmeter readings in the tabulation. Open the switch S. Replace the capacitors C1 and C2 with different values as given in the tabulation and verify them by following the same procedure. Let us verify the measured value with calculated values. Calculate the capacitive reactance Xc using the formula Xc is equal to 1 divided by 2 into 3.14 into 50 into 6 into 10 raised to the power of minus 6. Xc is equal to 530 ohms. Calculate the current using the formula I is equal to V by Xc. I is equal to 240 by 530. We get it as 0.45 amps or 450 milliamperes. Verify the calculated value with the measured value. From this, it is clear that when capacitors are connected in series, the reactance increases, so the current decreases, whereas in parallel, the reactance is lower, so the current value increases. Let us discuss the grouping of capacitors in combinations of series and parallel circuits. Take three capacitors, namely C1, C2 and C3, and let the values be 2, 4 and 6 microfarads respectively. Connect the capacitors C2 and C3 in parallel. Connect capacitor C1 in series to capacitors C2 and C3 as shown in the circuit. Calculate the total capacitance using the formulas as follows. Add the values of capacitors C2 and C3 as they are connected in parallel. 4 plus 10 is equal to 10 microfarads. Now, the circuit consists of two capacitors, 2 and 10 microfarads. Now, substitute the values in the formula. C is equal to 1 by 1 divided by C1 plus 1 divided by C2 since they are connected in series. C is equal to 1 by 1 divided by 2 plus 1 divided by 10. Then the total capacitance value is 1.66 microfarad. Now connect the AC voltage source 230 volts 50 Hz to the circuit, a moving iron ammeter 0 to 1 amps and an on-off switch S, all in series with the circuit. Connect a voltmeter V 0 to 300 volts in parallel to the circuit. Connect another two moving iron voltmeters V1, V2, each ranging from 0 to 300 volts. V1 is parallel to C1 and V2 is parallel to C2 and C3 as shown in the circuit. Energize the circuit by closing the switch S. Note the ammeter and voltmeter readings in the tabulation. Calculate the value of capacitance reactance Xc. Xc is equal to 1 by 2 pi Fc. Substitute 3.14 for pi, 50 Hz for frequency, and 1.66 microfarad for C, since we already calculated the total capacitance as 1.66 microfarad. So we have capacitance and reactance Xc is equal to 1918 ohms. Calculate the current using the formula I is equal to V by Xc. I is equal to 240 by 1918. We get 0.125 amps or 125 milliamps of current. Calculate the voltage V1 across C1 and V2 across the C2 and C3 from the formula V is equal to I into Xc. Similarly, V1 is equal to I into Xc1. V2 is equal to I into Xc2. Xc1 is equal to 1 by 2 into pi into F. Xc1 is equal to 1 by 2 into 3.14 into 50 into 2 into 10 raised to the power of minus 6. Xc1 is equal to 1592 ohms. Xc2 is equal to 1 by 2 into pi into F into C. Xc2 is equal to 1 by 2 into 3.14 into 50 into 10 into 10 raised to the power of minus 6. Xc2 is equal to 318 ohms. V1 is equal to I into Xc1. V1 is equal to 0.125 into 1592. V1 is equal to 199 volts. V2 is equal to I into Xc2. V2 is equal to 0.125 into 318. V2 is equal to 39.5 volts. When you add V1 and V2, you get 239 volts which is approximately equal to the input voltage of 240 volts. Ensure the calculated values are approximately equal to the measured values. From this video, I hope you can connect the capacitors in series and parallel as per requirements.
Thank you for your time. Have a good day.